Right. Okay. Can I start then?
Yes, please start.
Yeah. Okay. So this is a piece of work that we did in the labs in the late 2020, and it is actually a little bit of published work as well. I thought I'll just share with you our experiences in building a digital twin, and also show you that it's not so difficult for you to build one on your own with free and open source programs. Okay, so all that people talk about high end tools are actually not required if you want to build something for very specific applications, and this was what we learned at the end. So my goal is just this. This is a busy slide. Don't worry too much about reading everything here. I just want to define what I meant by all the open and free and open source software that we are referring to. What you see on the extreme right is of interest to us. Okay, and let me also tell you that this should go back before COVID-19. 2018, around that time frame, I had this idea of trying to create an extremely small chamber which is temperature controlled. I don't know what actually happened, but then we were also looking at vaccines inside then. You have to believe me for what I'm saying. And that was much before all this COVID stuff actually started. The origins for that was also because I had a colleague who was working on trying to look at blockchains and how to associate blockchains with chambers for carrying vaccines and all that. For some reason, we were discussing that. And then it hit upon me that my knowledge in simple electronic systems we should be able to build a very small chamber. So what you see on the extreme right is a small chamber. What you see on top are two fans. Am I right? Those two fans essentially are these are basically Peltier devices. Okay, and we are trying to cool this chamber inside if it gets heated up, and if it is too cold, we try to heat up. So how do we heat up? What you see on the left side, bottom down there, is one fan, and below that fan is actually another Peltier, and that Peltier is essentially heating up the system. And you can see this chamber is pretty small, and we are interested in modeling this chamber in its completeness, not just in terms of just acquiring data from it, but actually performing a CFD model of this simple chamber inside. Now, that is one thing. Second thing is we are also interested in looking at the temperature profile inside the chamber once it is closed. So you need a thermal sensor which sort of looks at all the temperature hotspots and all the complete profile of the chamber inside. So what you see two things. One is measuring a spot temperature, and that is with the temperature sensor. As you can see on top, it is fixed to the lid. And down below, there is a 4x4 thermal sensor, which essentially is getting a map of the complete temperature profile inside that. The thermal profile is available there. Okay, so this is of interest. How do you build this? How do you make a digital copy of this? And how do you look at, let us say, what is known as a what-if analysis of this? Looking at catastrophic instances of this is what we are actually interested in. So this is actually my problem statement. Okay, and to get to this problem statement, we need to look at the physical model, right? So this is a physical model. You have to build the complete physical model. You also need a simulation model, right? So if you are doing CFD simulations, you need CFD model. Then you need an automation framework. Several of the mundane activities which are repetitive by nature, you should be able to sort of automate that. And that part is done by the automation framework. So that's what we have in our experimental setup. What are the software programs we have used? Well, we used OpenPLC. Essentially, you're trying to control the maintain a certain range of temperature for inside this chamber. So we thought we should do it with a PLC because, again, industrial systems use a lot of industry 3.0 plus kind of environments continue to use PLC systems. So we thought let's try and control this temperature with a PLC system. And we looked at open PLC because we don't want to mimic everything free and open, right? So in a university, so open PLC. But open PLC has its own limitations of what it can provide in terms of interfaces and so on. So we had to build our own PLC. I'll show you those pictures of those as well. Then you need an orchestrator. That is, you're collecting humongous amount of data from within this chamber, and you're uploading it to some cloud-based system. And that cloud-based system is essentially giving you a lot of data points from this particular chamber, which is on the right. And so you need an orchestrator. What kind of, how do you interface between the digital world and the physical world? You need that orchestrator. We'll come to that. Clarity will emerge as we go along. Then you need to create the geometry of this, right? You need to have a complete geometry. Again, you need open source tools. We don't want to go in for any licensed tools. So we said we'll look at Freecad, and Freecad is easily downloadable. You can download, install. Okay, it's hard to learn, but then it's free. I mean, you sit in your free time and you can learn it. A good thing is it'll give you a lot of Python code behind. So if you have to embed it into some system, it is very easy. And the Python code, if you run it, will already render and give you these kind of nice, beautiful pictures, which we will see as we go along. SimFlow is essentially the software for the CFD. OpenFOAM is actually the API, which is the actual engine for CFD. And then ParaView is a GUI kind of interface by which you can visualize. And UiPath Studio is an RPA tool. Essentially, it is a robotic process automation tool. We will see all of that as we go along. Okay, so this is about this slide. Any questions? You're more than happy to ask at any instant. Otherwise, I'll keep going. I'll assume that you have understood all what I'm saying. Now, my own definition of yeah.
You want the questions, I have to allow them. Would you like?
I don't hear you well. Your voice is getting is breaking.
Oh, what I mean is I have to ask questions.
I'm sorry. Can you repeat?
Should I allow them to ask questions? Allow their mics.
Oh, okay. So it's up to you. How do you do it normally? I'm okay to go till the end and then take questions.
No, as per the speaker's comfort.
I have no problem. If people want to ask, they can ask. If people want to ask, they can ask. No problem. All right. So let's move on. So here is what I was looking up several pieces of literature on this digital twin, and it was actually quite intriguing to see what how people keep defining it to their own convenience, right? And this is my understanding of what digital twin is and why we need it. Okay, so it basically you should be able to get an exact digital copy of the physical entity. So this is my motto. Several people don't agree with this first bullet itself because they feel that why do you need an exact physical copy? Because I need it because I'm an electronic engineer. So I can build the physical system as much as I can build the digital system. So for me, it's pleasurable to see both parts looking at each other as a mirror copy of each other. Several other people look at not that they are wrong, but they're also, that's another view, right? And I'll show you some examples of the other view as well. Now, as we go along, you see that with live data coming from that physical system, this digital or cyber clone could be manipulated to act as a simulator. So it becomes, this is important. You must get live data from the physical system. It should be fed into whatever model that you have in the digital form. And now that becomes a nice simulator. And it's a simulator of what? It can be of a physical process. It can be of a factory floor. It can be of a machine as simple as a solenoid valve, a motor, pump, etc., or any bigger systems like, let us say, an airplane engine, or even the airplane itself, or maybe the airplane cabin, or maybe the airplane's environment control system, or whatever. It can be anything, subsystem, large system, a large piece of equipment, and so on. So this is what you could do with if you get the live data in. Now, in my opinion, it has to satisfy, if you want to call something a digital twin, it should have two requirements. One is it should ensure that it captures the context correctly. You buy a solenoid valve. Let us say that valve is meant for water applications. Then you want to repurpose it and put it for air applications or some gas application. Then you should know the context under which that particular valve is being used, right? So it's very important to capture the context as much as possible, where under which the physical entity is functioning. This is very important. The second thing is it should be you should be able to get all the data. You should be able to replay the past. What happened, let's say 5 minutes back. I want to know what was happening to that, let's say a valve, which suddenly started malfunctioning. What happened 5 minutes back? So I need to get a replay of the past, and I should be able to simulate the future as well, input, and I must be able to do some time-based behavior modeling and so on. So that's another important requirement that a digital twin should be able to provide. Okay, apart from these two, most important thing you want from a digital twin is the what if analysis, right? You want to do predictive analytics, something that is a big area right now. And you also want to look at dynamic recalibration, which essentially means you built a model and you are looking at a copy of that model that was built. And then you see that the model is slackening in its behavior, and you may have to do some dynamic recalibration, which actually affects back the manufacturing process itself. That means you go back to the drawing room and say maybe the material is not good, the thickness should be increased, or we should use some other composite material, and so on. So it should basically be able to give you super amount of insights even before you start a mass manufacturing of a particular part. So all of this should actually happen. I wanted to show you a little bit of what exactly people have been doing in the digital twins world for smart manufacturing. What they do is to go beyond the virtual workshop, right? You have to do that. When you talk about a workshop planning and simulation of systems like logistics simulation or factory layout simulation, you get a nice, beautiful virtual workshop model, no doubt about it. But these geometric models actually are not all that great, because they actually don't have anything to do with the physical world, right? So you need to connect somehow and have a co-fusion between the physical and the virtual world. So just making a virtual workshop model is not going to take you very far unless you are able to fuse it with the physical system. So that's basis essentially is the basis of integration of this virtual workshop, which is meant for logistics, factory layout simulation and all that. You actually have to connect it to the physical system. Actually, all of that means you have to collect humongous amount of data and you have to fuse this data. So the big takeaway is digital twin means a lot of data, which you have to somehow put sensors, you have to collect data and use that for further processing. Okay. And in the smart manufacturing world, people have different views of what a twin is. So here are at least 3 different things that you can build. You can build a product digital twin. You can have a production digital twin. You can have a performance digital twin. You can be looking at different perspectives at what you want to actually build as far as your end goal is concerned. Okay, so this is a very important thing and a big takeaway for people who are looking at twins. What is it you're looking for? Actually, this term digital twin is pretty old, actually, right? So the name was coined in 2002, but Apollo 13 already had a digital twin version, which the NASA engineers had already built, and they had super amount of simulations of the real world data which they played into that simulator to help the astronauts come back safely to Earth. So a lot of work was already done. So it's just a fancy name today, but it's been there for several decades now. And you have to just look at the fact that IoT has spiraled out with so many sensors and a lot of data that you can collect from systems have actually helped us to build these models as accurately as possible. Okay, so the basic idea of the twin is to see what might happen, what are the what if conditions, and then the trials on the digital twin should be possible without having to test potentially very expensive changes on the real world counterpart. Think about an airplane engine. You don't want to touch the engine, but you have collected all the data from the engine and you want to look at some aspect of that engine. Now it becomes a lot more easy for you because you have a fully captured model of the actual system. So expensive changes can be you don't have to, all the expensive changes that are required on the engine design, actually you can do it on the twin part itself. Condition monitoring, very important, because you're looking at remaining useful life and so on. And of course, it has to reduce the unplanned downtime and all that. I'm sure several of you know what that is. Let me go quickly into the construction of such a digital twin. As I mentioned, it should have the look and feel of a twin should be largely dependent on the application. The factory floor twin obviously has to be laid out exactly like how the real factory is, with the ground truth distances mapped to whatever pixel distances on your display systems, right? And when we talk about construction of these twins, physics-based models are important. They may be created whereby the physical model describing the system is available, and you'll be able to look at the behavior in real time and predict the future behavior as well, right? So this is one sure way of constructing digital twins. Another way is to just look at data that is coming as data points from the system, and you use a lot of humongous amount of data that you have collected previously. You use it for training a model, and the current measurement that you have will be based on all the predictions and all the data that you collected previously, and you predict the future trend. So you see there are two diametrically different ways of doing it. Physics model is doing something in one way, it's the data driven model is doing it in a slightly different way. I strongly believe, I don't think either this or that is the way. I think you should have a hybrid approach. Your initial model should be developed on multiphysics for an as designed system, and adapt it over time using the data driven approach and as it is performing. So when you talk about digital twin, I strongly believe we should have both elements, and this is a hard problem because CS and IT guys may not really like to go into the details of the multiphysics part, and the electronic guys don't want to go so much into the data driven part. But I think the win-win actually happens when you combine both, and I think a select few of them would be very comfortable in both the worlds, and I think the benefits are out there. Real world issues like aging, drift, and all that are best captured when you look at the usage rather than on all these assumed operational conditions of these systems. I took this slide from MathWorks, and this is not my slide, which you see on the left, but what I wrote on the right side is something that I've been thinking about. So when you look at data-driven models, we'll clear this quickly so that we can go into the physics-based models, right? So if you look at the data-driven model, there are three things that come up to your mind. Please look up Matlab. It has a lot of these toolboxes out there. If you look at the extreme right, lifetime data with or without covariates, this is essentially talking about accelerated life testing. So you have, let us say, a system in your hand, and you are interested in doing an accelerated test, maybe subjected to harsh conditions, run it several thousands of times, and you develop what is known as a survival model. That is one way of building a twin for different applications. Like let's say you're interested in remaining useful life and so on. The second is, think about a railway train, and there is a rim, and there is a lot of wear on that rim, and it is degrading as time passes. So you have a degradation model. It's also a nice way to build the remaining useful life prediction and maintenance. Then the third one is actually the extreme left, which is the similarity models. You have multiple machines manufactured with the same specification. Maybe it's also from different vendors. But then an ensemble of similar components are used in order to predict the remaining useful life of the system. So people, engineers actually use one of these methods depending on what they are looking for. And use these analytical tools and methods for arriving at data-driven models of digital twins. I would like to take a simple example of a data-driven model, which I did in the lab, okay? And I'll show you what I see here, what we did here. Look at this solenoid valve. The right side one actually shows you a valve which is part of a water filter. Okay, if you look at any of these standard Eureka phobes and all these machines, they have these valves for allowing water, cutting off water, and switching on the other systems inside a water purifying system and so on. So these valves are used. Now, suppose you want to repurpose these valves, right? And these valves have very specific applications. You have water feed in one case, you have liquid dispenser valve, you have irrigation solenoid valves and so on. So valves have different applications. Supposing you wanted to, let us say, take a water feed valve. It's again a hypothetical example. You want to take a water feed valve and use it for liquid dispensing. A valve is a valve. Can I use it? Yeah, I think you can, provided you have the required specifications that are met. And but you have to be careful, because water feed valve may not give you the same kind of performance that was to be when you put it to a liquid dispenser system. But there is still this possibility. So that's what we were trying to explore in our labs. Can you repurpose? And what should you do if you have to repurpose in order to see how successful that system will work? Basically, you have to collect, you have to instrument the physical system with sensors and collect humongous amount of data. And then you create a model of this solenoid valve. So you can see now I've created a data-driven model of a solenoid valve. And I have repurposed that valve for a different application. What you get is something like this. Okay, these are all lab measurements. Okay, so these are so you can ask me, I can explain in clear detail what we did. What you see on the left side is I don't know if it is a good valve, it's a new valve. Okay, so I'm a bit careful here. And what you see on the right side is an old valve. It's we don't even know whether it's malfunctioning. Okay, it was still giving you that sound, tuck, 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 it was doing that sound. So I don't know if it was malfunctioning. But what I know for sure is if I look at the current waveform, the x-axis is time and the y-axis is the current. If you look at the waveform, you clearly see that there is a back EMF developed at this point, and then it should dip down and then go back and settle down to have the holding current. There is the on current of the solenoid valve, right? This is the off current and this is the on current. So this on current should be there, number one. And then when it dips, you actually know the delta I. From the top peak it went, back EMF came from that peak to this down, and then when it goes back, this delta I you should be able to know. So this is what we found, that it should actually repeat each time the valve is operated. So you can see that we went up to 2700 cycles and we started extracting this current waveform. Then we took another old valve and then we started looking at its current waveform. You can see that first of all the current when you keep it on, but I mean the solenoid is energized, but when it is off, it's actually not taking the required current at all for some reason. And when you actuate it, you can see that there's a huge visible waveform change, which we could easily observe and then say that it's perhaps not functioning the way it should have, right? So if you connect a current sensor, a simple current monitoring sensor to this solenoid valve, it's very easy to connect it to this solenoid valve, you will get this beautiful waveform. And this waveform itself will hold, a wealth of information for you to process. And you give a waveform like this to any of the data analytics, data science people, they'll actually do 100 different things to show you and make you understand what are all the possibilities of whether this is a good valve and how long will it survive, what is its remaining useful lifetime, and so on, right? So all those analysis is now possible, which essentially means that health index calculation has become a latest thing that people are interested in for all the different components. So now what do we conclude from this? We can say that yes, you could perhaps do repurposing, but watch out. If you repurpose and you find that the valve is behaving like the right side one, whereas your expected behavior is like the left side one, then maybe the repurposed valve should perhaps be replaced again. So it's time to replace the valve because it's not functioning. It worked for, let us say, 1,000 operations, but then soon after it stopped working. So it's not performing as it is expected. So I think there is enough room for you, all of you, to keep looking at such systems and look at how to innovate around what you have around you. Okay, so this is just one simple example which I thought I will drive you away from what I wanted to actually discuss today. But this is a good model for a data-driven model. Now, if you collect humongous amount of data, how do you get it onto an orchestrator? Is there a standard architecture? First takeaway, please look up Eclipse Ditto. This is a digital twin orchestrator. You can see that on the left and bottom point are all the real world systems. You have all the devices and all the sensors, all the IoT devices, embedded devices which are giving out data. And they are all giving out data, and this data is being communicated using some protocols like MQTT, COAP, AMQP, and so on, without getting into details, but these are all IoT protocols, right? And then you can have users on the internet, and those users may actually be connected through a web app, which you see on the extreme left. It could be on a phone as well, in which case it can be a mobile app. And these are requiring data. They require data in a different protocol. They require it in HTTP. But what you are acquiring data is either through MQTT or one of the IoT protocols, which means this orchestrator has to do the job of a gateway service, which essentially does some kind of protocol translation before it can actually make available this data to the people sitting on the other side somewhere and working and looking at their web app systems. Okay, then you have other protocols which are there like AMQP and so on. Without going into great detail, just to tell you that WebSocket is a very interesting protocol. If you haven't worked on it, it's something useful. We have used this extensively for maintaining real-timeness between the physical system and its associated digital copy, which is the digital twin, and we use WebSockets quite extensively for that. There are latencies, but our applications are okay to work with those kind of latencies, and we'll show you as we go along. Now, the first thing is I showed you that chamber, and the chamber has to maintain a certain temperature range inside. This is about the physical system. The physical system has to maintain a certain range of temperature. How do you do that? I did mention that we were using PLCs because in manufacturing industry moving from 3.0 to 4.0, there are PLCs which are widely used. Can we deploy, can we get an open PLC system? Can we put our own PLC system? Can we program it using the standard programming languages that are well documented in 61131? What about ladder logic? What about function block diagram? What about ST? Can we use them? And so on was what was occurring to us. Because we wanted to create a tabletop version and we wanted to ensure that it is industry compliant. So PLCs is something that we wanted to seriously examine. Now the question we asked is, can we maintain the chamber's temperature to that set point using the PLC? And how does the programming block look like and how difficult is it? So we had to learn a little bit of PLC programming in order to ensure that we can control, we can monitor and control the chamber and use different protocols to get this data out from the physical system. You can see that this is PLC programming. All the control loops, if you are interested in PID, PI, or just P loop or whatever you want to do, or just on-off control, all of that is easily programmable. Open source, easily programmable. and you can get your system to be controlled in a closed loop manner. So closing the loop should be very, very simple with PLC systems, and that's essentially what we did with all the open source tools that are available. And of course, Modbus is another protocol which industry people use them extensively. You can see that PLCs also talk Modbus, and it gives you, it fits very well, right? So you have query response and so on, and gives you the kind of guarantees that TCP offers you. And so essentially we used open Modbus, and I'll show you where exactly this Modbus protocol is being used to fetch the data from the sensors. And as I mentioned to you, WebSockets is a very exciting protocol for real-timeness. It runs on top of HTTP. You start the connection with HTTP, then switch over to WebSockets, and then you start getting messages in quick time. So it's bidirectional, message-oriented, and it's streaming. And essentially, it's a message-oriented communication, which is quite efficient. And we found this to be extremely convenient to use. This is the PLC board that we made. This connects several things that might be occurring in your mind. What you see is extreme right are the virtual twins. We use Freecad to create the geometry of the system. This is the electronic copy. This is the physical board, which I already showed you. This is, if you open, I showed you that this is the heater. This is the temperature sensor. There are thermal sensors as well to look at the profiling. These are the cold side, which is kept on top. And then this is the physical system. Now this physical system is being controlled with this board. This board actually has another computer on top. You see this cable, and then there's a computer here. This is a Raspberry Pi, which you can buy for 2,000 rupees. And this is the Open PLC board, which we made in the lab. We plan to open source it. So if you are interested, combination of this board and this Pi, if you buy, you will have a full-fledged PLC system that you can build on your own for your own control applications. Okay, so this is something that we can discuss post this talk, that we want to actually make this open source. By the way, this has nice features. It has several ADC ports, and then it gives you all the digital interfaces and a set of relays to control loads and so on. So it's quite feature rich, I would say. So this is essentially what we built for even before we could build the twin. What was also important is this little thing about robotic process automation. Several of you already know it perhaps, but I want to emphasize that this is a very, very important upcoming thing as we go along. In fact, Gartner says that it will touch, this technology will reach 2.4 billion next year. Essentially, it is a very simple, dumb thing, right? Any rule-based repetitive task that humans do can be carried out by software robots. Okay, so you basically want to mimic human action by a software robot entity. What are these actions? It could be data entry, it could be data extraction, it could be report generation, it could be call center activity. See, when someone, if you're sitting in a call center, some customer calls, what does the person do? He takes the phone, then says, give me your ID, then he clicks on something in the computer, then that record of that item will show up, and then some forms will have to be filled up, some fields have to be read, and then they'll have to look at the status of whatever that they're answering to. Regular stuff. It's the same thing. The next customer comes, you do the same thing for the third customer. So these kind of things are all pretty boring and mundane tasks. Same with onboarding employees. What do? You ask them to go and meet the HR. HR will give a set of forms. The same set of forms are given to each employee that comes. It's a regular activity, regular standard thing that we'll have to follow. So all these things are all just mundane stuff. You go as a fresh employee to a company, that HR will sit in front of a computer and then click a button, and then one set of forms will come out. Medical forms, then address related information and blood group related, some medical tests, and those forms will show up, right? All these things are pretty standard for every employee that comes, new employee. onboarding employee, this process is done. Can you not look at how to automate all of this by just looking up at the keystrokes and the kind of operations that are done by the operator? Essentially, RPA does that. And it's huge business, by the way, because you're not going to get labor anymore. So for these kind of mundane activities. So essentially, it's a piece of software layer, okay? Looking at all the repetitive tasks that are done, and then it automates. You don't have to learn any programming to do this. You just install this RPA tool. It will already do some profiling. You run it for, let us say, 15 days or 1 month on your computer. It will already tell you, hey, these are the repetitive tasks that you're doing. I'm going to set up a workflow for you. You accept that workflow and you're done. Okay, that's as simple as that. Believe me, you don't need to know any great programming. Okay, it can also run other Python scripts and all that, but you don't have to be superly tech savvy to run RPA, to run a software robo. And we thought we should also integrate that. See, these are all elements which are going to come in a modern factory, right? RPA, PLCs, then digital twins and so on. So it should be sort of a comprehensive solution that we move towards. There are other tools that you need to create your model. I mentioned to you about SimFlow, OpenFOAM, Freecad, and ParaView. Essentially, the CFD software is the SimFlow. Then open source OpenFOAM essentially is the real engine. It's nothing but the library which offers you all the CFD simulation. SimFlow will allow you to create and import the mesh. So you can create a mesh in Freecad and get SimFlow, use SimFlow to import that mesh of the system that the chamber that you have built. So Freecad is nothing but free and open source general purpose parametric 3D tool. ParaView is open source multi-platform data analysis and visualization and all of that. So essentially everything is available. Okay. The RPA tool essentially which I just described is from UiPath Studio. Okay. UiPath Studio. It's also free for single users. For companies, they have a different offer, but if you are trying out as an individual, it's totally free. Okay, so you can try all that. I mentioned to you that I'll link up where exactly Modbus is coming, and this is where the Modbus comes up here. In a nutshell, this is how the whole physical system looks. You have a Peltier cell for heating, you have Peltier cells for cooling. I showed you that pictures already. There is temperature data coming in, analog input. Then there is Modbus, which is essentially running between the OpenPLC and the Raspberry Pi. And then I mentioned about WebSockets for bidirectional real-time transfer of data from the physical system to the virtual system, which is essentially passing through the orchestrator, which is called the Eclipse Ditto. And then you have HTTP based web app where that's where the user is sitting and looking at this complete chamber. So creation of the Freecad tool, quite straightforward. We did this. We have created this using the tool that we downloaded. We got these Python scripts. You can see that if you run the Python script, it nicely renders it. This is the real model and the virtual model. They look pretty close, and we had to now look at how to move on to create the twin version. What you see here is a commercial PLC unit. Okay, this is what we tried to begin with, but then we quickly replaced it with our own PLC unit. Okay, and the Raspberry Pi is still the same because this PLC unit board is quite expensive. So we decided to do it on our own. Okay, and this is the Peltier cell that we used. Essentially the Peltier cooler as it is called. It's used for both purposes, for heating as well as for cooling, depending on how you pass power to it. So we use this Peltier cell. Now I will explain to you. If there are no questions, I would like to pause here. If there are no questions, I'll go ahead and explain a few things that we did in terms of creating the digital twin. The floor is open for a minute or two to take questions. No one has a question?
Are you able to switch on the mics?
Hello, sir.
Yes.
Afternoon, sir.
Good afternoon.
Sir, can I know a bit more about how about this Modbus will be operating between the PLC and the Raspberry Pi, sir?
That's the
You elaborate
protocol.
it, sir?
That is the protocol that runs between any data that you want to extract from PLC. You have to use TCP, Modbus over TCP.
Sir, that protocol will be like a MQT or our HTTP, sir, in between those two?
Modbus uses TCP. It's neither
TCP,
HTTP or anything. It uses
Oh,
TCP.
oh, TCP, sir. Okay.
So Modbus is the application layer protocol. It in turn uses a transport layer protocol called TCP.
TCP. Fine, sir. Thank you, sir.
Okay, if there are no questions, we'll move on. You can see now what you see on the right side, extreme right side.
Hi sir, good afternoon.
Please ask me.
Yeah, sir, I have a quick question. Suppose we are doing some sort of simulation work using Matlab where we are designing the PID control. And my question is how to integrate those PID software algorithms into this hardware. Is there any scope and how to do it?
You can definitely use Matlab Simulink software for creating your PID loops. Now, how do you translate the PID loop that you created in Matlab onto your target system? It might have to create a C code or something, and that C code is what you will fuse onto your controller, isn't it? Physical microcontroller. That's one approach. The approach that I'm mentioning here is to use in industrial systems. They don't use Matlab for running actual PLC systems. You actually go out and buy a PLC. Now, OpenPLC allows you to download the PLC software, run it on something like a Raspberry Pi commercially available system. In fact, Raspberry Pi is available as a commercial version also for industrial applications. You can run it on that. And then inside if you once open the GUI of the PLC, you can create all your control loops nicely, including timing, right? Because PLC gives you that advantage. So one approach is through Matlab, which you mentioned, and that is a little has to be done in a particular way. That is, you convert it into C code and download it onto like an executable onto your controller, microcontroller. The other is to run a PLC code like what I showed you.
Okay, sir. Thank you.
Thank you. Okay, what you see on the extreme right is the Open PLC, which you can Google and find out for yourself. It's a amazingly nice software, and the PLC is essentially controlling the Peltier cell hot system. Every time the temperature goes low, you need to switch on the hot side. Every time the temperature goes high, you have to cool it down. So you have the extreme right Peltier cell cold system. And for that, you have to keep sensing the analog, you have to keep sensing the temperature. So you have the temperature sensor connected to the Open PLC system. This information will have to be passed on to Raspberry Pi over Modbus, and that's where Modbus over TCP comes. And then that information essentially can be conveyed back through WebSockets, via WebSockets to users who are on the remote side using the orchestrator called Eclipse Ditto. All right, so this is essentially what I wanted to tell you. The left side is about the hardware. Everything what I've shown here, I've already described. So I'll move on to the next slide here. Here is the physical model. Look at the extreme right. You have user input, which is actually the desired range over which you want to work. And now you have a measured value, right? You have the ambient temperature, which is the measured value. Now, if the measured value is greater than the desired, you have to ensure that the cold system is turned on, right? It is it's on the higher side. So essentially the left side loop is doing a cold system on. And the opposite is true if it is the other side, the other way. You switch on the cold subsystem, right? You switch on the hot subsystem, so that this condition can be satisfied. This is greater and this is lesser, right? This is less than the temperature, set temperature, and this is greater than the set temperature. So essentially, this is the automation control loop which we put up in place, and we started running this system. And how often were we collecting samples? Every 50 milliseconds we were collecting the samples. Okay, so the desired temperature is repeated every 50 milliseconds. In other words, the PLC loop was set to 50 milliseconds. Here is a simulation model. This is interesting, right? So you have to completely simulate this, CFD simulate this little system which you built using Freecad and imported it using SimFlow. And we set it up as a simple heat transfer problem. Essentially, you have for the heater side, these are conduction. These are two conduction loops. And then this is a convection loop here. And it just goes out. Air goes out. The hot air goes out here. There's a fan here. There's a fin here. This is the heat sink's fin, right? And this is the sink base, and this is the Peltier chip here. Similarly, for cold subsystem, you have the Peltier chip here. You have conduction, and then you have convection. So if you use it like if you cast it into a heat transfer problem, you can easily solve these equations and obtain the single value. You can get the math model essentially of this complete system. So Freecad and OpenFOAM, SimFOAM and ParaView I already mentioned. So I'll move on. Now look at the automation framework. I mentioned to you about all the dumb activities, repeated activities that we do, and how RPA UiPath Studio can be used. Here essentially there are three workflows that the UiPath Studio actually created for us. What is the first one? It simply says you take the user input simulation model where the user input generates the CFD, geometry, mesh, solver, turbulence modeling, thermophysical properties, operating conditions, boundary conditions, initial conditions, and simulation output. This is the easiest first level, not easiest, I would say the simplest thing that the RPA tool actually found that we were doing once we got the input from the user input. Once we got the user input, this is all what was happening. Essentially, you're talking about the sensor value coming in, right? From the physical system, you got a sensor value, you run it through all of this, and then you get an output. The second workflow is designed to download it, to download the real-time data from the Eclipse server to the local PC. In other words, the physical system is uploading to this orchestrator, and from the orchestrator, which is nothing but Eclipse Ditto, you're downloading it onto a local PC. All the sensor values, you're getting it down. So the communication between the physical model and the digital model is established using this second flow. The third workflow essentially is the opposite. See, a model is no use if you are able to, you don't want the digital twin to just follow the physical system. You also want it to be interesting, right? You also want to ensure that you're able to actuate the physical system. If there's a catastrophic incident that happens, which you're able to predict well ahead in advance of the actual catastrophe happening, then nothing like it. You actually wanted to tell the physical system to do a few actions so that the system is kept safe. So that is the third workflow. You're uploading data back to the physical system. So these are the three workflows that RPA was able to catch and was able to automate. Now this is the math model. As I mentioned to you that the math model was developed for hot and cold subsystems. What is very important in this math model is the math model runs taking data from the physical system. Okay, so this is very important. So don't look at these equations as just something that was arrived at, but these equations actually take data from the physical system and then they compute using the physical data that is available to you. Okay, so this is the key thing, and these are pretty straightforward equations, and I haven't done anything. We haven't done anything great here. you can go back to first principles of specific heat formula or Fourier's law, which is for heat transfer and all that. If you apply them, you'll quickly arrive at these equations. These four equations, these two here and these two here, are the basic equations which actually will run by taking the data from the physical system. Now here is the overall system architecture. What is actually happening? I mentioned to you that the Eclipse Ditto is the orchestrator. There is a user input which comes from here, and the Eclipse Ditto takes the data. It gives it to the physical system, and then the physical system is running. The physical system gets the data. The model gets the data from this loop, gets downloaded through an RPA loop. It comes to this local system. As I mentioned, UiPath Studio is the RPA tool. Then it can also do a few things after taking that. It will run through the math model. If there are anomalies, it can come back here and give it back to the Eclipse Ditto so that it can go back to the physical system and actuate the physical system. All of that is possible because now you see you're getting data ahead. You're getting data through this loop, running your math model, finding out anomalies, giving it to UiPath Studio, which in turn goes back in this arrow form to the orchestrator. Orchestrator simply gives it to the physical system, which will get energized, which will get actuated. So you avoid catastrophes. Now you not only do that, you get the local data, then you also run a simulation. Why? Because supposing you are interested in temperature, you are not only interested in finding out the chamber's temperature inside, but also you are interested in the profile of the temperature profile. That is possible only if you run the CFD all over again. For every data point that comes, you run the CFD, and then you look at you visualize the CFD and see how exactly the profile inside looks like, and verify it with the 4x4 sensor that we use for looking up at the chamber. So you can see all these elements are tied up with this little picture here. Now I will explain to you about one scenario, and perhaps after that you can also ask me questions. There is one scenario. So after having built all of that, we wanted to try a simple what if scenario, right? You want to do a what if testing scenario. And what is that what if that we want to do? We want to ensure that the two-way communication between the twin and the physical system is actually controllable, right? So that's where the real strength of the twin actually comes in. You're able to predict, you know that it is going to be a catastrophic situation, and then you know that if that catastrophe happens, the chamber might blow and in fact may explode, and therefore you know that you want to avoid that part, and then you quickly give a command to lower the temperature. I'll show you all of this. Essentially what we did is for analyzing this what if, we took the case where the chamber is already at 35 degrees and it is rising to 45 degrees. Okay, it is rising to 45 degrees and 40 degrees is the upper limit. That's what we wanted to do. 40 degrees is the upper limit. Now let's see how exactly it happens. Look at this. What you see on the right side is the temperature profile during hot subsystems operation. I mentioned to you inside the chamber we have a 4x4 sensor which is looking at the complete thermal profile. That means you have 16 pixel elements looking at different points in the chamber, and it is giving you the temperature value. We didn't want to plot all 16. We took only 4 of them. We took cell 5, cell 6, cell 9 and cell 10, and we plotted them in different colors. Since we are getting data live from the physical system, we ran our math model in the digital twin, and our math model showed us that it has to go at this instant. Let us say take 300. It should have actually touched this temperature, but it did not. All through inside the chamber, you can see all the colors were much lower. So this difference is already there. Now question is, why did this difference come? Why is this math saying it should be here, whereas this 4 colors are lower? Clearly, there is leakage. This is talking to you in terms of the ideal situation. In spite of modeling it as closely as possible, still the math model is a little away from the idealities. And therefore, one thing that occurred to us is that if you want to have a perfect replication of the digital twin, you must control leakages. Is this not already very good input? Supposing you are looking at a twin and you're looking at leakage of gas. This is a good indicator. It's already telling you that, oh my God, my twin is telling me that there is a leakage in gas. Maybe the Vizag gas tragedy could have got avoided if we had a twin system and we knew that gas was actually leaking, styrene gas was leaking. Right? So these are some of the strengths of the math models. So very important, if you are able to model it good, math model is good, you're getting physical data, nothing like comparing the two of them to come to some useful conclusions. Same with the cold system. The cold system is also not close to the actual reality, right? So you will see that the cold system is cooling faster compared to what the math model is actually saying. The reason is you have two peltiers which are connected for cooling. So cooling is much more, we wanted to make it a lot more rapid. So that is the reason why it is lower than the other one. But you know, as long as the relationship is maintained, you should not have, is basically a standard offset. It's an offset error, a systematic error. That systematic error can be easily corrected if it is a, if you know what it is. So essentially it's the random errors that are difficult to catch. Systematic errors are easy to correct. So this is the comparison of the physical model and the math model. I also mentioned to you that you need CFD for every data input point that we take. So we ran the simulation model. You can see that the 30 and 40 degrees that we had planned are all showing up here. These are all some of the CFD plots that we had put up here. Okay, so 40 degree is 313, 30 is 303.15 Kelvin. So it's out there. Essentially, the heat transfer solver uses this steady state conjugate heat transfer, which is was used for to model the physical system essentially inside the CFD. Great. So yeah, here is one other interesting result which I wanted to discuss with you. The look at the picture on the right. It's telling you that if the temperature is rising, x-axis is time, the y-axis is temperature. If the temperature is rising in a particular way, in that gradient way, in the gradient that you see there, it's obviously going to touch 45, right? That is the prediction that you're getting. With basic data points that are available from here, perhaps, already you can predict this and you can also predict these dots. So right at the 100th second, maybe, or even early, you actually know what is the trend and how it is going to go up. It's not going to go up like this, neither is going up like this, but it's actually going up like this. So this you already know. And this is your catastrophic point. You don't want it to go beyond this point. Okay. And here the real strength of the twin comes in. You're getting data onto the digital twin because this data is going to the twin through all the process I showed you, orchestrator and so on. And then the twin looks at the data, runs the math model, and then quickly realizes that, hey, this is going to go like this, and then it's going to touch 45, in which case it might explode. Then what it does, it now instructs the physical system by giving data back, by giving an instruction back, saying that you better turn around, don't touch. The moment you touch 40, come down. It will give a command requesting the physical system to step down because it knows for sure if it had left it, it would go and hit 45, in which case it can be a disastrous situation. Therefore, before the physical system could reach the decision point, a signal is sent to the physical system to redirect back to 35 degree in order to maintain safety. So you can see that safety is really maintained and is a very good end product of what a digital twin can actually do for us, right? So here is some simple discussion I wanted to tell you, that what are the limitations of what our system can do. I mentioned to you about the CFD simulator. See, the CFD simulator has one, because it's open source, there are some limitations as well. It takes only one input. Every data point you have to run the simulator all over. Okay, it's not the kind of thing that you are very comfortable, because if you are doing real timeness, you want to continue the simulation from there, right? Because you have to quickly evolve over time to see how the temperature profile inside the chamber is maintained. So therefore, this is one limitation at the moment. But yeah, but then I think there are better tools now like Open Modelica and so on, where you may not want to do CFD in the way it is being done, but use different kind of mathematical tools to get you to that point. So I think there are ways out there as well. Okay. In the simulation model, we can compute one layer of heat transfer at a time. This is another thing for those of you who know, heat modeling. You'll realize that this is also a little bit of a limitation. Okay, it's you compute one layer of heat transfer at a time, and there is no control loop built into the SimFlow software that would allow us to run the hot subsystem and cold subsystem simultaneously. Well, this is really not a big problem, but I wanted to bring it to your notice. Okay, so if you are doing hot, you don't really do cold and so on. But ideally, you want these features to be available if it's a commercial product, right? So that's one thing. Now, UiPath Studio, which is essentially an RPA tool, currently you only have Windows version. Okay. The problem is the physical system, all that Raspberry Pi and all that we put was running Linux-based system. So working between Windows and Linux is not so easy. So we had some issues there. Okay, so that's another thing. But not everything is lost. What we learned from all this is that we can build twins easily from open source software. We can start looking up Open Modelica and other related open source software as well. And we started to start using this in a much more exhaustive manner. And we do have a model of a twin that is coming up in our labs using Open Modelica. And all of that I would like to discuss as we go along. Maybe in future meetings we can discuss how to use Open Modelica, modeling electrical and mechanical systems, bond graphs and so on. This can be done as we go along. Okay. So essentially this is the capsule I wanted to discuss. We still have 15 minutes. I'd be very happy to take questions. Shall I show a demo? Can I show a demo?
Please.
Okay. Maybe we will spend a couple of minutes showing a demo. So let me stop sharing this and show you a demo of the physical system. Give me a minute and I will put that demo for you. Can you see my screen?
Yes.
Can you see the video?
Not yet.
No, sir. Yeah, yes, sir. We can, sir.
Can you see the video? Okay.
Yes, sir.
This is the digital twin temperature control demo setup. Sorry, I can't take you to my lab because of the prevailing conditions, but surely you can see. Web page for user interface. You can feed in the required thresholds. Okay. You see now thermoelectric cooler is on. This is all the Modbus monitor program that is running behind. PLC server with data logging. All of that happening there. And temperature control chamber is shown here. This is the PLC. This is the Raspberry Pi. That's the chamber of interest, which we have here. You can easily build with all these open source tools This is the Peltier cells for cooling with heat sink and fan. This is the heater inside. There is a temperature sensor. There is a thermal sensor inside, which is giving you the profile of the complete system. So, folks, you can actually build it all by yourself without much of a problem. You can actually build these systems. So that's all I have from my side to show the demo. I'll be happy to take questions.
You may please, thank you very much, Prabhakar. The participants may please raise their hands and ask questions. Mr. Fagun?
Yeah, good evening, sir.
Good evening. Go ahead.
Sir, instead of open form, can we use ANSYS for CFD simulation and all?
Perfect. You can use ANSYS. You have to pay license, no?
Yeah, actually we need to pay. But yes, but sir, instead of open form, it is quite versatile and proper data can be get from ANSYS also.
Yeah. See, there's always a trade-off, right? So you have several of these tools which are available. ANSYS for sure, but you have to pay the price.
Yeah. Yes, sir. Thank you, sir.
Thank you. Ms. Lalita Kondapalli?
Professor, one question I have. Can this same concept be used for predicting the reliability? Okay, one is this can be used during the product development to see whether the fail-safe mechanisms and all are being taken care or not. On the other side, for manufacturing, so can we use it for coming up with the reliability values like MTTF, all sorts of things? Instead of actually testing on the product, can we use a digital twin for that, which would definitely save cost and time and all other things?
Absolutely. You have asked a very good question. We were thinking about this particular aspect. It's true that if you have models for all the components that are used, then you can easily create a reliability model for sure. But the problem is you don't have reliability models for all of them. There is one book which I was referring to, and that book had models for simple things. But this is a superly good question. I think people have neglected the reliability modeling part. Surely it is possible.
Can you suggest me that book name?
So this is a book by there is a book by Professor L. Umanand on power electronics.
Okay.
If you look up that book, one chapter there, he is talking about the reliability of electronic components. There is a limited amount of literature on the reliability.
Okay.
So
yeah.
please do look up that book.
Yeah. So one question again. When we say that if we have the models, it is easy to really come up with the reliability figures and all. But in the beginning, you said that in your application, that really the valve, when we feed in the data with the input and the output, and some of the models can be calculated by the softwares, by the say CFD analysis or whichever software you're using. Can we take that path where we don't have the model, but we just put huge amount of data for every input that we give, what is the output and what are the other parameters or characteristics of that device? If you can just feed in and come out with a model, and that can be used for reliability prediction, and if that is possible, what could be the error in these values?
Very nice. Very nice. I really liked your question. I did mention that. I also mentioned to you that this area actually maps into the data-driven models for systems. For example, if you recall, I showed an extreme right picture of one way of doing it. is the accelerated testing. Okay, that is something that you actually want to arrive at a model, isn't it?
Yeah,
I am sure
correct.
whoever has arrived at reliability model would have done it with certain experimental way only. You can't just sit back and say, let me look at silicon failure, then let me look at some other failure. That would be one way. Another way would be to hard build these models by a lot of experiments and lot of studies. The solenoid valve I have used did not do any CFD. I did not do any CFD on that. What I did was very simple. I connected a current sensor to the current probe sensor to the to one of the windings. In fact, it's non-invasive. You can use Rogowski, things like that. So we just captured the current profile, nothing else. That profile itself is throwing away huge amount of giving you humongous amount of information on the lifetime of that valve. You can see that, right? On the right side, it was completely destroyed.
Yes,
That
yes.
dip never was there. So now your question can be answered in that way. Supposing you see a smaller dip, and as you progress, you keep seeing smaller and smaller dips. At one point, you don't see any more dip. That is something statistical methods can be applied. You can do some regression and things like that, and then arrive at when are you likely to not see a dip anymore. And that's perhaps what is that's why I wrote very carefully. I'm not sure if it is malfunctioning. It's an old valve. I am not
Yeah.
sure.
Okay, got it.
Yeah, so I
Thank you,
think
sir.
your this is rich in problems. Very good, things that you can do. Once you are getting data, you can build these models for sure.
Thank you, Professor.
Thank you. Subhashri Roy. Yeah. Mr. Badri.
Hi, this is Badri Narayan and Professor, good evening.
Good
I
evening.
just want to understand, as we know very well, digital twin is between the physical model to digital model. Do you have any experience in the digital model instead of going into your finite element model related models? Now we are talking about CFD. I know that you have Excel boundaries and also what is the input you are giving to the model in terms of what you call high temperature, low temperature, etc., and all that. So can we try to use what you call modelica models? That means your different physical models available in various libraries and build your model. But there could be a challenge like how to create the external environment very close to what exactly happening in the physical model. That is a challenge. But do you have any experience on that?
Yes, yes. Okay, good question. I will. Open Modelica is something that we have started working on,
Mhm.
and we have, as I mentioned to you in passing, that modeling need not be through the CFD route anymore. It need
Okay.
not be. I mentioned this already. You can use bond graphs, for instance.
Okay.
Okay, and we have actually attempted to do bond graph modeling of ours. The same chamber is actually now built in Open Modelica. We started looking up at Open Modelica. We
Okay.
also have an ECS model in Matlab because Matlab gives you the power of, see, Matlab also has become IoT enabled, isn't it? You have
Yeah.
that ThinkSpeak now,
Yeah.
the ThinkSpeak channel which you can establish. And I will show you one picture, maybe that will help. Give me a minute. Huh?
Yeah. Thank you.
Just quickly download and then show you. Okay, so Let me quickly show you. Yeah, this one. Okay, let me share my screen again. Can you see my screen?
Yes, thank you.
So this is a room ECS. Okay, this is completely modeled in Matlab Simulink. This is an environment control system. What you see on the left side is this IoT enabled. Matlab is already IoT enabled. We have channels here, and you have input and output. Here is your GUI dashboard. You want to maintain a certain temperature inside the chamber, and we have built this model using now not anymore the tools that I mentioned, but purely Matlab.
Okay.
Matlab is the GUI. Matlab is the controller which we have. Someone asked about Matlab PI control and all that. You can use PI control Matlab. This is one way of doing it.
Okay, thank you very much.
Yeah, and then you can go on. You see room ECS digital mode. This is HVAC system. Then you have the PLC board. You can connect IoT things channel, and then you can connect it back to the twin. So you can see this twin is here. The physical system is on the one side. The right side will actually have the digital model on the other side. So you can see that different channels are there. Data coming from the different channels.
Yeah.
So it's doable. I mean, these are very good areas to work on. I showed you just one way, and I showed you a way by which you can do it with zero cost. We don't want to pay too much money when we are experimenting with commercial software. No, so this is one way.
I got your point. Yes, you are right.
Thank you very much. Dr. Sitaram.
Yeah, good afternoon, Dr. Prabhakar. We had a wonderful presentation by you.
Thank you.
Very enjoyable. I'm from CPRI. We have conducted large number of energy audits. I think we have to actually refine our approach, energy audit, with respect to certain critical phases using the methodology expressed by you. I think that will happen in next 1 or 2 years. So we'll definitely stay in touch with you. Thank you very much.
Sure.
Thank you, Dr. Prabhakar. It was really impressive.
Thank you.
Yeah, thank you.
There's a question from Subharshi Roy in the chat. He says, as you mentioned, UI path is not supported in Windows and RPI as Linux operating system. So is there any application for virtual machines or hypervisors? Can you please shed some light on it?
Oh, okay. Yeah, that's true. Actually, it's the UI path is supported on Windows. Okay, and it is the other way, right? So it's the whole system we built was on Linux, and UI path actually is from
Windows. Sent it again. Yeah, supported on Windows, not Linux. Yeah,
okay, what does she want? Okay, let me just open this. Is there an application for virtual machines or hypervisors? If yes, can you please shed some light on it? Actually, we haven't done so much work on this particular aspect, Subharshi Roy. One thing I can tell you is, you should be able to, latency becomes an issue in all these systems. You want the digital twin to be very, very closely following the physical model. These VMs may create additional latencies, which might be an issue. So this could be one answer, but we haven't personally worked on, trying to see why VMs should come into the picture for digital twins.
Thank you very much. Aruna Sarkar.
Good evening, sir. Sir, I have a question, sir, that in the robotic process automation, there is a point called mimic human action by the software entity. So, sir, can you elaborate it more, sir? How can the human action be mimicked by the software?
Oh, absolutely. I can give you a nice example. See, I have seen these people working in call centers. Okay, there is a guy sitting in front of a computer and he's waiting for a call. Let us say he's attending to a customer. Customer calls. Once the customer calls, what happens? This guy says, good evening, your name and all that. He asks for some information. Let's say this is about printer service as a simple example. Okay, he's offering a printer service. It's a service that is being offered in the call center. Now this guy goes and then clicks on HP, and who the call center person who's offering the service goes and clicks on HP. Then he pulls out a data sheet, and then next thing is he'll read a particular line, and then he'll copy paste it into an email and then send it to that email of that person. Okay, he says, you read up this is your problem. If you do this, your job is done. Now think, so this is what he does. Now another person calls. Another person has another problem with some other printer, let us say, and this is a HP call center. So what is this fellow doing? The second time he's doing the same thing. He takes the name, he opens another file, something he'll copy paste, put it into email or give an answer and then close the matter. This is one good example. Another example is onboarding employees. You go and stand in front of the HR. HR will say, come on, sit down here, clicks a button, one health form will come. Then one application form will come. Then one ID form will come. And another form, some 15 forms will come, will get printed out. He or she will hand over that forms to you. And then you take that form, you start filling up, and then you do a few things. Now the question is, if you now click one button and say a new employee has come, why do you need any human there? All these forms can be printed out directly even without a human, isn't it? This
Sir,
is
if any
boring.
document is, sir, if any document is missing for the candidate, then sir, what will they do, sir?
No,
Sir,
that is okay. See, at least let me answer your question this way. Those are corner cases. Straightforward, if you automate, many of the repetitive tasks which are there can be avoided. That's what I meant. Not that you are replacing the human completely, isn't it? Let us say if the load of the human comes down to 60%. Are you not happy?
Yes, sir.
So that's the idea.
Thank you.
Thank you, sir. Yes, sir.
We did the same thing. See, in our case, I'll tell you, I think that is one way. Another way to connect is to, in our case, what is the RPA doing in our case? Same old boring thing. There's a physical system. Temperature value comes. Temperature value has to go into the model, into the math model. The math model has to compute, has to give out a number. The same input data that came from the physical system will have to go into the CFD. The CFD will take in and then it will give it to SimFlow. From SimFlow, it will go and pull up the Freecad geometry. Then it will do the simulation. It will give you the simulation CFD output and it will give you a number. Why do you need a human? You can't even, in fact, need a human to do this repetitive task. Let us say every 1 minute, there is a data point coming from the physical system. Just think about the workload for the human who's managing it. Every minute he has to keep doing the same thing. Get the data, feed it to math model, get an output. Get the data, feed it to the simulation pipeline, get the output. Again, by the time he does that, again next data point has come. So it's so boring, right? So any boring, repetitive tasks which are mundane by nature, which don't need any great intelligence, offload it to software robots so that they will take over the businesses.
Yes, sir. Understood, sir. Thank you, sir.
Thank you very much. That was a very good answer. Mr. Ganesh Jambali.
Good evening, sir. After this presentation, I am so much interested in digital twin field, sir. Sir, can you please share some book name from where I can learn about digital twin, sir?
Actually, I haven't come across any book. There are sufficient number of IEEE papers. Okay, and there are sufficient number of IEEE papers in this area. Maybe I can see if we can. These are under copyright. That is the problem. If I have a rough version of some paper that I have, I will share it with our CEFC. You can collect it from there.
Okay, sir. Thank you, sir.
We have some questions in chat, Dr. Prabhakar. We're
Yeah,
out
sure.
of time. Would you like to take the questions?
In the chat, huh?
Close. Yeah, we close with the existing questions.
Oh, I don't see Sujay Kumar. Is it okay? Just let me go. So, Subarshi Roy be finished. Then Sujay Kumar. Sir, what is the scope of adaptability of digital twin when will update physical systems? Sujay, what do you mean by this? What is scope of adaptability of digital twin when will update physical systems? Sure. See, don't ever think about a digital twin being a dumb system just following the physical system. No. If you have the power of the data much ahead of you, you can do regression and you can do all kinds of data analytics on it. You have the power of what is actually happening to the physical system. You will have to take the responsibility of telling the physical system, don't do this, don't do that. You are going into a catastrophic situation. Otherwise, what is the use in getting to know the model ahead in time, right? Therefore, that delay should be, it depends on the application by and large. So that's all I can say. Coming to Ashutosh, how to deal with modeling system consisting of several subsystems. Exact model may be computationally expensive. In that case, we go for approximation. In such case, how to ensure reliability of the physics-based model? Perfect answer, perfect question. Very, very difficult question, Ashutosh. This is a research question. I have no answer for this. That's why you break up the model into manageable parts and then you model only those simple subsystems first. If you make it into a very large one, then you will have a problem. That is true. So exact model